Gauss's law is a fundamental principle in electrostatics that relates the electric flux through a closed surface to the net electric charge enclosed by that surface. It is especially useful for calculating the electric field for charge distributions with high symmetry. Gauss's law states that the total electric flux through any closed surface, called a Gaussian surface, is equal to the net electric charge enclosed divided by the permittivity of free space. The formula is given by phi underscore e equals the surface integral of E dot da, which equals Q underscore enclosed over epsilon underscore 0. The total electric flux is measured in Newton meters squared per Coulomb. The integral represents the surface integral of the electric field over the closed Gaussian surface. Q underscore enclosed is the net electric charge inside the surface, and epsilon underscore 0 is the permittivity of free space, approximately 8.854 times 10 to the negative 12 c squared per Newton meter squared. An important application of Gauss's law is to find the electric field at a distance, r, from an infinitely long, straight wire with a constant linear charge density. The process involves several steps. First, choose a Gaussian surface. Due to the cylindrical symmetry of the infinite wire, a cylindrical Gaussian surface of radius, r, and arbitrary length L, coaxial with the wire, is chosen. Next, evaluate the total electric flux. The electric field points radially outward from the wire, assuming positive charge density. The total flux through the closed cylindrical surface is the sum of the flux through the curved surface and the two flat ends. The flux through the flat ends is 0 because the area vector is parallel to the wire's axis, while the electric field is radially outward, making E dot da equal to 0. For the curved surface, the electric field is perpendicular to the surface, and its magnitude is constant at a fixed distance, r. Thus, the flux through the curved surface is E times 2 pi RL, where 2 pi RL is the area of the curved surface of the cylinder. The total electric flux is then simply E times 2 pi RL. Third, calculate the enclosed charge. The charge enclosed by the cylindrical Gaussian surface of length L is the linear charge density lambda multiplied by the length. This gives us Q underscore enclosed equals lambda L. Fourth, apply Gauss's law. Substitute the expressions for total flux and enclosed charge into Gauss's law. Finally, solve for the electric field. By canceling the length L from both sides, the final expression for the magnitude of the electric field is E equals lambda over 2 pi epsilon underscore 0 r. This result shows that the electric field magnitude is directly proportional to the linear charge density and inversely proportional to the perpendicular distance from the wire. The electric field vector is directed radially outward for positive charge and radially inward for negative charge. Understanding Gauss's law allows us to efficiently analyze electric fields in symmetrical charge distributions, a powerful tool in electromagnetism.